Hi, good morning, everyone. Good afternoon, good evening. My name is Maria Luisa Toledo from IBGE and from the UN Regional Hub for Big Data in Brazil. And it's a great honor to welcome you to the second day of our webinar on Earth observation and artificial intelligence for agricultural statistics, which is organized in partnership with the UN-CEBD Task Team on Earth Observation and FAO, the Food and Agriculture Organization of the United Nations. This event is part of our ongoing webinar series on climate change indicators. I'd like to inform all participants that the webinar is being recorded and will be shared with the community afterwards in our website. And before we start and dive into today's agenda, I'd like to briefly recap what we covered yesterday. We had the first session of the webinar. We opened with welcome remarks from Lorenzo De Simone, who set the stage for our discussions on how EO and supervised AI methods are being used for crop mapping. We were then joined by an excellent lineup of speakers. Mr. Sven Gillians from GeoGlen gave us a global and regional overview of AO for agriculture monitoring, highlighting key initiatives and the importance of harmonized methods. Mr. Zoltan Santoy from the European Space Agency introduced the World Serial and the Sem4Stat projects, showcasing open tools and pre-trained models that support the National Statistical Offices in crop mapping. Mr. Christoph van Tricht from Vito walked us through supervised classification techniques and provided practical insights for those interested in implementing these methods. And after a short break, Mr. Eduardo Vasquez from INERI presented Mexico's experience using YO to define the agriculture frontier as part of their census work. And finally, Mr. Ian Nunes from IBG and from EFLO wrapped up the technical talks with a presentation on AI-based field boundary detection and its integration into a statistical process. It was a rich and inspiring session, and we are very excited to continue the discussion today. So let's now move into day two. Today we'll focus on the statistical integration and advanced AI for yield forecasting. And to open our session, I would now like to invite Mr. Lorenzo De Simone, who is a technical advisor at the FAO. Lorenzo, thank you for being with us today again, and the floor is yours.
Thank you very much, Maria and colleagues, and thank you to all the participants who are joining. So you gave an excellent summary of what has been discussed yesterday, whereas today's agenda, let's say, brings a shift in focus. So essentially from Earth observation mapping to how we actually convert the Earth observation outputs into statistical indicators such as area estimates, and how we structure our workflows to make these operational. So we will begin today's session with Sophie Bontemps from UC Louvain, who will demonstrate how we estimate crop areas using regression models applied to Earth observation maps. Then we will have Claudio Stenner from IBGE, who will discuss the Global Geospatial Statistical Framework, the GSGF, and how it supports the alignment of geospatial and statistical infrastructure, which are especially critical for NSOs. Then we will have Professor Gilberto Camara, who will provide a hands-on example of satellite image time series, the SITS processing, reinforcing the importance of temporal analysis in agricultural monitoring. So the motto is time first, space after, as he will explain. Then we will hear from our colleagues from China, presenting on use case and contribution to the handbook, before wrapping up with a presentation and a panel discussion on the Earth observation to statistics. So what are basically the challenges, an overview of the challenges and of the opportunities. As a final note, so our objective today is to link Earth observation products with statistical workflows, continue building and the shared foundation for the UN handbook on remote sensing for agricultural statistics. My encouragement is really that of let's continue together with the same collaborative spirit, ask questions, challenge the assumptions, and help us to shape tools and guidance that will serve the broader community. Thank you.
Thank you, Lorenzo, for set the scene so we can begin. And our first presentation today is by Dr. Sophie Bontemps from the Université Catholique de Louvain in Belgium. Sophie Bontemps is a senior scientist and project manager at UC Louvain. She specializes in remote sensing and land cover monitoring with a strong focus on agriculture and environmental applications. She has played a pivotal role in several European Space Agency initiatives, where she has contributed to both methodological development and product validation. Her expertise supports global efforts in sustainable land management, climate monitoring, and agriculture statistics. Sophie, thank you very much for being here, and the floor is yours.
Thank you very much, Maya, for the nice introduction. I will share my screen. And buenos días a todos, y gracias a los organizadores por darme la oportunidad de estar hoy aquí con vosotros. Es un placer. I will continue in English. So I have been asked to give a talk about the estimation of crop area using maps based on remote sensing data and using regression models. So let's start. So, of course, agricultural statistics is something very important. This is not to you that I have to explain that. So it serves multiple purposes. Some of them are here, but of course, this is not exhaustive. Monitoring of agricultural policies, informed decision-making for food security, for sustainability assessment, and so on and so on. What is very important when we talk about the agricultural statistics is, of course, its accuracy, how reliable it is, how robust it is. This is also the aggregation level it is related to. Is it statistics which is valid for the country, or can we also have information over smaller units like the regions, the counties, the districts? And last but not least, the timeliness. So the value of the statistics depends really on when it is out and it is available. So traditionally, without using remote sensing data, the approach from the National Statistical Offices, as soon as I know, so you know better than me, but if I have to recap it, to summarize, the principle is to make a survey and then to go and to interview, to publish the statistics. So the country will be probably stratified, and based on the stratification, a sampling frame is designed by the NSO. The sampling frame can be area frame, list frame, point frame. And this sampling frame will decide where the samples to be visited are allocated in the country. Then the samples are visited by enumerators. They can call the farmers, they can go to the field once during the season, twice during the season, and they collect a lot of information. This talk will focus on the acreage of the crops, but of course the survey are much more exhaustive than that. And then there is a huge work in the office to quality control the data and to interpret them, to derive the statistics and to make them publicly available. So this is how it works, and we are convinced, and we are demonstrating the fact that remote sensing can be a nice complement to the field surveys for agricultural statistics. And so we are not at all claiming that remote sensing data can replace the field surveys, but can complement to get improved statistics. So this is the basic statement of the talk today. And the way if we focus on the acreage estimate, the way it can improve can be diverse. We can talk about what the cost efficiency. So we can use remote sensing data to maximize the statistics accuracy, to get a lower variance associated with the acreage estimate, or to reduce the cost of the production of the statistics, because here what will be presented today is the use of data, satellite data that are open and free. I will come back to that later. EO data can also improve the granularity of the statistics by allowing the disaggregation over smaller administrative areas. They can improve the timeliness, and they can also support the sampling design, either by allowing moving to an area sampling frame or simply by improving the allocation of the samples in the surveys. So the work I will present today belongs to the Senforstat project that was already introduced yesterday by Zoltan from the European Space Agency. So Senforstat is a project funded by the European Space Agency that aims at coupling Earth observation data with statistical surveys for improved statistics. So Senforstat is an open source toolbox that can be run on the cloud or locally, and that is using free and open data. So Sentinel-1, which is a radar sensor, and Sentinel-2, an optical one. It is using these Sentinel data, and also it is needing agricultural surveys. I will come back to that later on. But we really need satellite and ground data in Senforstat. And then it is producing a set of remote sensing products that will characterize the crops on the field, maps, crop growing metrics, yield estimation. And at the end, what we are doing is that we will combine these remote sensing products with the statistical surveys, not any kind of agricultural survey. This must be a statistical survey. So we combine both to get improved statistics. One slide about the Senforstat toolbox. So as I said, this is an open source system which is using SAR and optical data, and it has been really designed for an operational production of crop products that will support the agricultural statistics at national scale. So the ambition is really that this toolbox can be used by the countries to make their operational crop monitoring and statistics by themselves. It is using Sentinel-1, Sentinel-2. The pre-processing of the data is included in the toolbox, and it delivers different kinds of products that will, again, characterize the crops. So we have cloud-free temporal composites with Sentinel-2 and temporal synthesis from Sentinel-1. So these are just images that correspond to a given period and which aim at being without cloud, so to understand the area and which crop is grown when. We will also have time series of spectral indices and biophysical variables. This is from that we will extract matrix to do crop type maps at 10 meters, also to derive crop growing matrix that will feed the crop yield estimation at different aggregation levels. So this is what we do from the remote sensing perspective in Senforstat. As I said, Senforstat is using remote sensing, but it is also using survey data. And it is important to mention that these survey in situ data are and remain the central piece for the agricultural statistics. So in Senforstat, the data have three purposes. So the first one is the calibration. So we need learning data set to train the algorithm or the model for the yield or for the crop mapping. So for that, we need a data set that will capture the entire diversity of the cropland and non-cropland classes, that will cover all the crop types of interest, even the minor crops. So not only if you are interested in the acreage of maize, for instance, just getting information about maize is not enough. You have to have information about maize, but also all the other classes, crop and non-crop classes of your area of interest. And of course, the data need to be well distributed across the study area, which is generally the case because NSOs are working with a statistical survey. The in situ data also aim at validating the products, so the maps and the yield estimation that we are generating with Senforstat. And just a side note that this is really important to have independent data set for the calibration and the validation to have a validation that makes sense. And the third purpose is to have in situ data for the statistics estimation. And this data needs to have a survey that is statistically designed. This is really important. We don't need that for the calibration. We don't need that necessarily for the validation. But if we want to do the statistics estimation, we need to have a statistical survey. As a side note, always controlling the quality of the in situ data is needed, mandatory, very useful. The prerequisite to be able to integrate the remote sensing in the process of agricultural statistics estimation is to have GPS coordinate at the parcel level, not at the household level. We need to be able to make the link between the crop and a point in the image, a place in the image. So a lot of National Statistical Office are working with list frame survey. So in the list frame surveys, usually they visit households, farmers, they do the interviews of the farmers and they take the GPS point at the farm. This is not useful. It means that we need more. We need to go to each parcel that is recorded in the survey and to have its location. This is really a prerequisite for the NSO who want to use remote sensing for the statistics. Usually there is not a big effort to include it in the survey, so it should not be seen as a blocking point, but it shall be seen as a prerequisite to take into account when we set up a pilot or a feasibility study. I will now show different use cases that we did in which we use remote sensing data to improve the accurate estimation through regression models. The first example is an example from Pakistan. This is a project that we did with the World Bank and ESA. And so here we have been asked to integrate remote sensing data in the agricultural statistics in the Sindh province. And in the Sindh province, the NSO was doing their surveys with papers. So there was no digital tools to collect the data. And so we started very from scratch and we designed a simplified area frame sampling. So this was the area of interest. So 4 districts are out of the province. And we designed segments, so primary sampling units, which are these yellow squares of 2 square kilometers. And inside, we asked the enumerators to visit 15 points. Additionally, so these yellow squares are what we call the statistical survey. And additionally, we ask them to do a windshield survey. So when they travel between the yellow, the primary sampling units, they take additional points and they collect data about everything. So the windshield survey aims at doing the map. And so you can see here the number of points that were collected during the field campaign, which lasted 2 weeks. And so this was done by the enumerators of the Ministry of Agriculture. With this point, we did a map. So the focus was the wheat map during the Rabi season, which is the main crop during this season. And you can see, I will not go into detail, but maybe just to mention, you can see the accuracy. Overall accuracy of 0.88 and the F-score of 0.85. So you might say, this is good, but this is not enough to do statistics. You're right if the objective, if you want to use the map only to do the statistics, this is not enough. But this is not the way we want to use the map. So having this accuracy is still useful and is still very useful to support an improvement of the statistics by combining the map with the survey. I explain here. So what we do is that we will combine the map and the survey, the map being spatially exhaustive. So we have information everywhere. Every pixel in the region, we have a map which says it is wheat or not. And we combine this spatially exhaustive information with the survey, which is unbiased. The map is biased because it's not perfect. I just mentioned that we have 88% of overall accuracy. But by combining both, we can improve the statistics. And how do we do that? For each primary sampling unit, we calculate the proportion of the crop of interest. And so here, this is the wheat. For the map, within these primary sampling units, we get 5,489 wheat pixel out of 10,000, which means a proportion close to 0.55. And in the survey, we have 9 points out of the 15, which are wheat, which makes a proportion of 0.6. And we do that for each primary sampling unit, and we can do a correlation with a regression estimator to quantify the map, the bias that we have in the map inside the primary sampling unit. So we are able to quantify how the map under or overestimates the crop proportion inside the sampling unit. And we can apply this correction through the model to all the cells to obtain unbiased, accurate estimates. And this is the results we got. So we have compared 5 or even 4 estimations. So the first and second one are the estimation from the crop reporting service, so the NSO, at the beginning of the season, and the final one at the end of the season after the consolidation and the second field visit. And they get this accurate estimate, which is not associated to a confidence interval. So this is an estimation without using remote sensing data. We can also just make an estimation also without using remote sensing data based on the statistical survey that we collected. And so the inference from this survey, we have slightly higher values with a confidence interval, which is a good point, but the confidence interval is high. Using remote sensing data, we can have the regression estimator, so the method I just explained, where we have a value which is very close to the estimation from the crop reporting service, a bit lower than the inference from the statistical survey. And what is very interesting is that with this, we have a confidence interval that is reducing. And this is the advantage of this methodology and of remote sensing data, is that you can reduce the confidence interval compared to another traditional method. I mentioned that the maps cannot be used alone. So a lot of studies are doing just pixel counting. So they do a map and they say, I count the pixels that belong to my class of wheat, and I have the area of the wheat. Of course, this is not correct because the map is biased. There are errors. So if there is no other way than doing the pixel counting, the minimum that needs to be done is to remove a bit the bias by correcting the estimation with the confusion matrix. But then you will get another estimation without confidence interval, which is not really robust and which does not information about the quality of the statistics. Last but not least, for this example in Pakistan, so the good thing was that also we managed to have a good timeliness for the statistics. So I showed the example for the Rabi season 2024, but we are continuing the work with them. And you can see that we get the statistics available a few weeks, 2 months after the end of the season, which are consolidated. So this is a really good point also for the remote sensing. We repeated the exercise in another project, which is located in Zimbabwe. As Zoltan mentioned yesterday, we are working in Asia, we are working in Africa. Unfortunately, we are not yet working in South America and Central America. So this is also an opportunity to be here because maybe after this workshop, we will have new projects, new pilots with some of you. So here, coming back to the slide, this is Zimbabwe. Zimbabwe, we have been working with the Ministry of Agriculture and the NSO. In terms of data collection, the NSO was doing a list frame survey, collecting the GPS at the household level, not at the plot level. And the Ministry of Agriculture was doing a lot of surveys, but very local surveys. So depending on the needs, depending on the studies, we had some data localized in some districts. So this was not really useful for the demonstration. And here, the requirement from the NSO and the Ministry of Agriculture was to go directly to the national scale. So we implemented a field campaign with them, following the same principle where you get statistical survey and windshield surveys when you were traveling between the primary sampling units. And you can see the number of points that were collected, which is of course higher than in Pakistan, but this is the full country. And at the end, it was not enough because the quality of the maps was a bit lower than what we expected. But this was in 2024. We have been learning for that, and we are continuing in 2025. And we hope that it will improve. At least they collected much more points this year. And so with these points, we did some maps again. The accuracy, I just mentioned it, to show that the accuracy, of course, is far from being perfect. And we applied the same methodology where we estimated the crop proportion within the primary sampling units in the map and in the survey. And with that, we were able to estimate the area for the given crops through a regression model. And so this is an example for the maize and for a grouping of the maize, millet, sorghum, which were confused in the map. And so you can see that using the regression estimator and the remote sensing data, we are able to decrease the confidence interval compared to a traditional inference from a statistical survey. But the decrease is lower than in Pakistan. So this was a bit disappointing. But after discussing with them, so we identified different things to improve, and the number of points was very critical. So there were a lot of crops with let's say a limited number of data that were collected, which means that there were a lot of confusion in the map. And so this is why we are rerunning this year, and we adjusted a bit the data collection protocol. But they were very interested in the results because so far they had not this information about the confidence interval. They were all from the NSO. And again, the timeliness was a good achievement because the summer ended in June, July, and in August, and we had the results published and presented to the NSO and the stakeholders in November, which was a good point. The last example I will show you is about Spain. So Spain is in Europe, and so not yet in your continent. But I have included it because Spain is doing is implementing this agricultural survey as an integrated list and area frame survey, and I think that this is the case for some countries in the room, and so maybe they can make the link with what is possible here. And so you can see here, so the integrated list and area frame survey makes that here they have primary sampling units of 700 by 700 meters. And inside these primary sampling units, they have polygons. And for each polygons, they get the label. But so it means that by segment, they get already the proportion of the different crop types and also the non-crop. So we have been using this information to do a map. So the map was not done at once, but we divided the country in 4 strata. And so this is the accuracy for one of these strata. No need to go into detail, but just to show the level of accuracy, which is not yet higher than 90%, even if the map was found quite good visually and also by the NSO. And so this is the regression, the area estimates that we get after the regression model, the regression estimator. So you can read the table, so color by color, which are the 3 main crops of this region, Castilla y León. And so for each crop, you get the quality of the map, which is the F-score. And you get the first line, which is the acreage estimation without remote sensing data, so using only the list and area frame survey, and the acreage estimation by coupling the remote sensing and the survey through a regression model. And you get that for the 3 crops. The first observation, we are very close in the estimation, so the confidence intervals overlap each other. But the main result is the confidence interval. So the amplitude of this interval is reduced by 3 or by 4 when you are using the remote sensing data. So this is also illustrated in the graph on the right. So you can see the big impact of the remote sensing data just doing a map that you couple, that you integrate with a regression model with the survey. And so here the effect is much more significant than in Pakistan and in Zimbabwe, because the data collection is very good. So the quality of the survey, the number of segments, the number of polygons they collect is very high. So this is what you get when you do this kind of integrated list and area frame survey. And this is in this situation that the impact of the remote sensing is the highest. So coming back to the contribution of the remote sensing. So as I have shown, the remote sensing data can be really useful to estimate the crop proportion within primary sampling units and then apply to the whole area with the regression models. Remote sensing data can also be useful. I will extend a bit let's say the list of good points for remote sensing data. So they are also very useful for visiting primary sampling units which are not easily accessible. This can be the case in areas of conflicts or in case of natural disasters where you cannot go to the field. And so then you can maybe just interpret the primary sampling units with the remote sensing data. Of course, you do not get the same level of details. You can make this interpretation for the easy crops, like the sugarcane, the maize, the cereals, but it will not be possible to discriminate between the cereal type, for instance, without the field visit. And there might also be a bias related to the resolution. So if we are still in the Senforsstat mood, we are using Sentinel-2 data at 10 meters. And of course, this 10 meters is a constraint, but this bias could be decreased using very high spatial resolution data, but then the cost is increasing also. Two other things I would like to mention before concluding. So the remote sensing data can also be useful for disaggregating the acreage estimates. So to get estimation over small administrative units. So usually if you are just using the survey data, you do not have enough sample to derive the estimates over small administrative units. In the case you have a good correlation between the map and the survey data, we can apply what we call the small area estimators regression models, which will allow deriving some statistics at small administrative unit with a confidence interval which remains reasonable, and I will show an example just after. And the last contribution of remote sensing data can also come in the sampling design, where we can provide information to allocate the samples in the best way for the sampling design. So for instance, in the case of a two-stage stratified sampling, you first need to, let's say, characterize your initial population. So in this case, the initial population is a kind of grid, and you will characterize each grid of your area of interest in terms of cropland intensity, if you are interested in a given crop in terms of this crop or in terms of other characteristics, and the list of characteristics depend on, of course, each country. So to do this characterization of the initial population, you need a map. So in this case, this is a crop type map. We are in Philippines and we are interested in maize. And so we will compute the proportion of maize within the grid cells. Here you get the proportion within each grid cells, and you can define the strata. And within each stratum, you will allocate a given number of samples. And so this is where remote sensing can contribute by providing useful maps that will improve this stratification that is the basis for the sampling design afterwards. And the other things I wanted to mention is the improvement of the sampling frame. So in Spain, we were asked to do an irrigation map, so rain-fed irrigated crops, independently from the crop type, because they wanted to include this information in the design to be sure that they have enough irrigated crops represented in the samples. The granularity, I mentioned it, so this is my last example. So here, this is an example still in Spain, where for the barley acreage, and we are at the municipality level within Zamora. So municipality is very small, and you can see that we are able to derive acreage estimate with a coefficient of variation, so an error, which is relatively, I would not say small, but acceptable for these small units. And so that is not possible if you do not have a map. So this is only possible through the small area regression estimators I mentioned. My conclusion, so some message to conclude. So remote sensing data can certainly complement traditional statistical surveys for accurate estimates. And the best way to do that is to use regression models, avoid using the map only and just counting the pixels. And doing that, you will be able to decrease the variance associated to the accurate estimates. Remote sensing data can also improve other aspects than this variance, the timeliness, the spatial disaggregation, and the sampling design. Within Senforstat, we have been working successfully in Spain, Senegal, Pakistan, Philippines, Zimbabwe, and we have other pilots just ongoing, and we would be happy to extend also our activities with some of you. A very important aspect also and message, something to remind always and always, the in situ data are really important. So remote sensing data will not replace the survey, but if you want to use remote sensing, this survey must be compatible with the remote sensing. It means that the geographic coordinates must be at parcel level and not at the household level. And that we must have information about the cropped classes, but also the non-crop classes. You can find some information over the Senforstat toolbox on the website. I will not be longer on that. And last but not least, if you are interested in trying this technology, you are most welcome. You can talk to Zoltan and Lorenzo, who are there in Brazil, and you can contact me by email. But just to clarify also that this is a midterm process, so we can, it requires time, it requires demonstration, pilot, upscaling, and capacity building. So this is not something that will take place within a season, but this is feasible, and I'm convinced that this is really promising and useful. And with that, I stop here. Thank you very much.
Thank you very much, Sophie, for the great presentation. It was really inspiring to see how remote sensing can effectively complement the agriculture survey data. And I'm sure that the examples from Pakistan, Zimbabwe, Spain, they show the value of coupling EO data and statistical surveys to improve the agriculture estimates, and especially with the use of the regression estimators, the impressive reductions in the certainty of the estimates. And I think for us, for Latin American and Caribbean region, these applications are inspiring. And as Sophie said, I also want to highlight the potential for future collaboration with Sophie and the other experts, particularly for applications in our region. So thank you, congratulations, and thank you once again.
Thank you very much.
Now we move on for our next presenter, Claudio Stenner, which is our colleague at the Brazilian Institute of Geography and Statistics at IBGE, and the UN-GGIM network. Claudio is a geospatial expert with extensive experience in integrating Earth observation and statistical data for policy and decision-making. He has served as a director of geoscience at IBGE, where he played a key role in advancing geospatial infrastructure and promoting the use of the Global Geospatial Statistical Framework, the GSGF, in national statistical systems. Claudio has collaborated with international organizations to strengthen the geospatial and statistical interface, particularly in supporting of agriculture and environmental monitoring. Claudio, thank you very much for joining us today, and the floor is yours.
Thank you very much, Maria Luisa. Thank you for the invitation to be here with you. Good morning, everybody. So I'd like to provide in my presentation a general overview about the GSTF, the Global Statistical Geospatial Framework, and how can be applied to agricultural statistics. That's my intention. I will share my screen now. Just a second, please. Everybody can see my screen? Nice.
Yes, yeah.
So, before talking about the GSTF itself, I'd like to comment about the general global landscape that you have now. You face to a climate crisis, and if you have a climate crisis, you need a different types of data, and you need a different approach. For example, in agricultural. And what kind of information, what kind of new information about agricultural we will need to face the climate crisis. We face also huge demographic changes. Some countries are aging very fast, and other countries still have a rapid population growth. How can you face to this? And also the fast urbanization, especially in Africa and some countries in Asia. This has a huge impact in rural areas also. And maybe you need different kind of information in these rural areas to face this fast urbanization. You have also a persistence of poverty in inequality, unfortunately. And all these things lead to a growth of migratory flows because the world is too unbalanced, so the migratory flows tend to grow, and is growing was in the last years. But the global landscape also offers a lot of opportunities to everybody. First, the data is increasingly better, more available, and cheaper. If you're thinking about the remote sensing data, this process is very fast in the last years. 1 or 2 decades ago, remote sense data is too expensive. It's not available in the quality that we need to produce good data. But now, in general, there is a lot of free remote sense data that you can use. Also, you have a growing availability of other sensors and Internet of Things that can impact the production of information. And in parallel with this, you have the evolution of AI and the capacity of processed information, because if the massive amount of information you need to increase the capacity, fortunately, this it happen also, and in even in cheaper and cheaper way along the time. So we have the global connection by satellite that can change a lot of things. Think when you think in collect information in the fields, especially in rural areas, because it's possible to provide an online connection to satellites when you are in the field all the time. That fact can change a lot of things. And also have increasing availability of your coding administrative registers. For example, land parcels registers. So when you think in data production, you have some key challenges. The first one is complexity in governance, because there is a bigger number of producers and interaction. So how can you deal with this? And you need to think in the governance. One thing that's very important: the data value is not predetermined. It's not something that when you have a data that has some value as a predetermined. And so you have to think in a user-centered approach to data cycle. How can you deal with this? And I'd like to highlight two dimensions of data value. The first one is the data linkage related more to the data preparation, the technical aspects and the governance. And the other one is related to data analytic capacity, how the consumers, how the people receive and extract information from the data, and there is a relation for geodata literacy and communication strategy. Now we have the GSTF itself. It's a general framework. It's a high-level framework intention to show basic principles and how can we integrate statistical and their spatial information. This framework was endorsed by Statistical Commission and both the GIM. So it's a bridge between the statistical words and the geospatial words. Let's talk about the principle one, the first principle of the GSTF, the fundamental geospatial infrastructure and geocoding. As I said before, the governance is very important, and relate to this and geospatial information, you have the UN Integrated Geospatial Information Framework, the IGIF, to help us to think in how can you provide a better governance and how can you integrate the geospatial information itself. So this is it's important to integrate this different framework in order to allow to avoid the duplication of efforts and provide a good system, a good landscape of information in the countries. We have also another UN reference, that's the Global Fundamental Geospatial Data Teams. There is different teams that's a part of this geospatial data teams set. And when you think in agricultural statistics, when you think in remote census, what team is more important? What team do we need to feed the models and to improve the quality of remote sensing data, to improve the quality of agricultural statistics? For example, soil data can improve the quality of statistics. River data also, rainfall data and road data and other types of data can improve the quality. Land parcel data also. So there is what other data can be useful to improve this quality. The key of the principle one is to have all this infrastructure, and preferably in fact it's better if you have the very local data, like for example address, household address, like I show you in this example, but also land parcel, but also the geographic coordinator of the rural properties and something like this. When you have this kind of infrastructure, geospatial information, you can after link the statistical information to a very local geography. And when you're talking about remote sensing is a very nice in terms of this kind of reflection, because you have already a very local information when using remote sensing. So in this example, you can show different landscapes in Brazil. These are in the state of Bahia, has a very big crops of soybean and cottons, and very few households in this rural area. In the other region of Brazil, in the south part of Brazil, it's completely different. In this area, we have very small properties, as you can see, with a lot of small yellow dots, just the image. In this other area in Amazon region, we can see households along the rivers, inside the islands, in the rivers also. when we have this kind of information, can produce statistics, for example, for an island, that maybe it's very useful to planning a better policy. And also a big city like São Paulo. So, some thoughts on agricultural statistics and principle one. First, remote sensing enables the production of information precisely located, as I said before. And that fact increases the value of information. If you have a local information, it can be used to local policy. It can be used, it can address more in a better way all kinds of necessities of the populations. So what's the necessary geospatial information infrastructure to agricultural and remote sensing? That's a question. I don't have all the answer. I have some answer, but not all the answers. Principle two. Principle two is related to how can you link statistical information to geospatial information, and also provide security in terms to guarantee the confidentiality, and after you can to allow the aggregation to this information to a set of common geographies. So that's the word. In fact, in general, we start with this. There's a geospatial word, there is a statistical word, and these two words are not linked together. How can you link these two words? With the GSTF and Principle 2, we can, in fact, link these two words, the geospatial domain and the statistical domain. And with this, it's possible to have the statistical microdata geospatially enable and produce very local statistical, for example. This is another example, and how power is when you link statistical and geospatial information in a very local way. This map show to use households and also the location of schools and health facilities. With this, you can, using census information, you can, for example, estimate if you need one more school in some areas, or the school is too much in this area because you don't have a child to go to this school, and the same with health facilities. And you can think also similar things in the rural world with the local information. Thoughts about Principle 2 and agricultural statistics, some questions, how to connect information on land parcel and crops, because sometimes this is not so easy. A big land parcel can have many types of crops, many different crops, and how to connect the crop information with political administrative boundaries. This is a kind of challenge sometimes because big crops can overpass the, for example, municipal boundaries or other political administrative boundaries. How can you fix this? Maybe crossing administrative boundaries with crop boundaries. And how to better integrate census data with land parcel and crops. That's another challenge with many dimensions. Principle 3, talking about the common geography. What's this? So it's an example from Brazil. Common geography is a set of geographies that the in general National Statistical Office or the National Mapping Office maintain with precise boundaries, updated with time, with standard geographic names, and to provide a better meaning of statistical. So you need many different geographies to do this work. In the example of Brazil, you have 44 different common geographies to improve the value of the statistics. It's a urban example, but I think can illustrate very well what I'm said. This example from São Paulo, a slum area and a very wealth area. They are both in the, they're very close each other. And a statistical example from Rio de Janeiro, as you can see in this map, the neighborhood of Leme. The neighborhood of Leme includes both a slum area and a very wealthy area. If you have the statistics from the people that has high education, we have the number of 42.9% of this neighborhood mixing favela, the slum areas, and the welfare area. But if you have the right geography, in this case, I can split the slum areas with the other parts of the city. The real statistic is in the slum areas, you have only 1.3% of the people with higher education, and in the other areas, you have 49.9% with the population with the higher education. So without this geography, in this case, the slum areas boundaries, it's not possible to have these statistics. In the same thing, I can see, I can tell about the rural statistics, the agricultural statistics, thinking watershed basins are very important geography for this, maybe biomes and other geographers can reveal others a lot of things in the related to rural statistics. With principle 2, it's allowed to show the information in a very small areas. And I'd like to share some thoughts about it with you. First, remote sense data can be easily disseminated across a wide range of geography. That's a very good thing. But I have two questions. What are the common geographies that give you more meaning and value to agricultural statistics? What kind of local agricultural statistics can be produced by remote sensors to complement traditional statistical collections? Because all the times you need to a better geographic disaggregations, and I think the remote sense can help to have a more granularity of the statistics in territory. Principle 4, about interoperability. I'd like to highlight when I talking about interoperability, it's not only technical interoperability, standards, etc. We have also semantic interoperability, legal interoperability, and also organizational interoperability. The technical interoperability, I think today it's not a big problem. Generally, everybody can read the information. There is a lot of open formats, open standards that you can use, like in this example. Metadata is very important also to guarantee the interoperability. Without metadata, you don't have interoperability at all because you don't know about the semantic, for example, of the data. That's another example, the integration between statistical and geospatial information using open formats. And some thoughts that I like to share with you. A major challenge, I think, it's a semantic interoperability in remote sensing. How to deal with this? It's not easy. It's really, really a big challenge. Also organizational interoperability, because in general, National Statistical Office do not produce the remote sensing data, and there is another organization that produce this, so that's maybe a problem of organizational interoperability. And I'd like to think as a common geography as a key element of interoperability, because if you have a very wide range of common geographies, you can put different data in this common geography, social data, economic data, agricultural data, and it's a way to integrate data and to guarantee interoperability. Principle 5, accessible and usable. I'd like to tell to you that to guarantee a principle 5 application, you need all the other principles. So in other ways, not to be able to apply the principle 5. The value of principle 5, the principle 5 covers relate to dissemination of geospatial information enabled with statistics. Thinking about how can we ensure the widest access and usage possible. And there is two key concepts related to this. First one is the accessibility, how we can make the spatial enabled data easily discoverable, available, and retrievable. That's the first key concept of the principle 5. The second one is usability. How can we ensure that the data is fit for purpose, trusted by user? Two key things, fit for purpose and trusted by user when thinking in usability. So my thoughts about the principle 5 story and the GSTF. It's a major challenge of semantic. Sorry, this is wrong. Yes, sorry, this is my mistake. My talks about the principle 5, how to maximize the use of remote sensing data for the common user. It's not it's sometimes because when how to convert a very technical product in a user-friendly product to guarantee accessibility and usability to the user. That's the challenge related to the principle 5. Some general benefits, I think, to implement the GSTF through agricultural statistics. First, you can guarantee more value for the statistical produced because you have different common geographies, and with this, it's possible to increase the value of statistics. You can also better planning the necessary geospatial infrastructure and planning this in a shared way with other statistical areas, statistical domains. You can provide a better integration between administrative records, land division, and also remote sense information and census information. We can plan in the accuracy of remote sensing service connect to geography for dissemination. The key point that when you start to do the remote sense working, we have to think in the user, in the final user. So you can plan in this, all of this thinking in the final user. And my final considerations. If you think the technical issues, interoperability, and the governance strategy, the UN IGIF is the main pathway because there is a lot of thoughts in this framework that can help cultures and institutions to improve this. If you think it should build interoperable and powerful integrated data lifecycle from planning to dissemination, the GSTF is an essential framework about this. Also, common geographies and the national address file include rural files. I think it's a very critical infrastructure to guarantee interoperability integration of different data sources because there is a lot of administrative records that are related to this address, so I think it's very important. And at last, data production must consider users from the beginning and be based on the perspective that value is not can be assessed ex ante. That's very, very, very important. Data values updated through the process. That's very, very key. Interoperability reinforce data linkage and offer a rich array of options for data use and gel data literacy and specific communication strategies that enhance data analytic capacities necessary to take advantage of the quality integrated and interoperable data. That's it. Thank you very much for your attention.
Thank you very much, Claudio, for the excellent presentation, for presenting the key challenge, the structure of the GSTF and its principles, and also for relating this with the work at IBG, with the 2022 census in Brazil, which really introduced this major innovation by georeferencing all the visited households, what represents a significant step for integration, geospatial analysis into official statistics. And the GSGF continues to be a key instrument in the integration of geospatial and statistical domains, especially in the field of agricultural data. Thank you very much. And so let's move to our next speaker, Mr. Gilberto Câmara. Dr. Gilberto is a senior researcher at INPE, the National Institute for Space Research in Brazil, and is a consultant for the Food and Agriculture Organization of the UN, the FAO. He is internationally recognized for his expertise in geoinformatics and satellite-based environmental monitoring. Gilberto served as the director of INPE and as the director of the Group of Observations, and he has played a leading role in the development of open source remote sensing tools such as TerraLib and TerraAmazon, and is a strong advocate for open data to support the sustainable development. Thank you for being with us, Gilberto. The floor is yours.
Thank you, Maria Luisa, and thanks everyone who is attending, and thanks the organizers for the invitation. So let me just share the screen here, and okay, oops. So the first thing I should describe you, we've been asked to give a sense of what is the SITS package. So first of all, the basics of the basics. The SITS package is an open source package, which is written in R and has a Python interface as well, and is available. Can you see my screen? Can you see my screen?
Yes.
Hello?
Yes.
Yes. Make it bigger. Okay. So this is available openly on GitHub. And the idea of the package is to provide an environment for working with satellite image time series. As we all know, I think that's been clearly shown in this workshop, time series are a key aspect of agricultural monitoring, or use of remote sensing for agricultural monitoring. So and also for land use and land cover in general. So what we have provided with SITS was a way for, let's say, practitioners and experts and researchers to use these data sets in organizing the open source data, which is available, open access data, which is available in many collections. I'll show you some, into what we call data cubes. Data cubes are regular coverages of the same places on Earth with regular times and with harmonized resolutions. For example, if you had sentinel bands, some of them are 10 meters, some of them are 20 meters, you can just organize them so they all are 20 meters and they all are covering the same area. Out of that, we obtain image time series, which are then merged with samples. These samples can come, as Sophie has shown, mostly from in situ surveys. We have also good experiences with a mix of in situ surveys and lab work by identification of in high resolution data. This is used to train algorithms, including machine learning and deep learning algorithms, and to produce land use and land cover maps. And SITS include, as something that was very much emphasized by Sophie and yesterday by Lorenzo, was the ability to measure uncertainty and measure confidence intervals on the data. As it became very clear, you should not simply believe the map and think it's right. The map has bias. So I'll basically start by showing some of the functions that SITS is available, and everything is available in a documentation which is available on the web. So if you type SITS book on Google, you should reach the site of the book on SITS. I'm showing you the latest version, but you have already, this is the version that is available on the web now, which is long discussion, all the topics. We are preparing a new version which includes access to Python. We should be ready by Living Planet Symposium. But this version already tells you a lot on how to do it. It's a step-by-step approach. The objective of the book is both to learn SITS, but also to learn how to work with big Earth observation data with satellite image time series. So it's not just a cookbook, but there's lots of discussion on what it means to have a data cube, what it means to access the data. So I invite you to take a look at the SITS book, which is, if you, like I said, if you type SITS, at least if I type SITS book on Google, you get immediately the book. That's it. So let me show you one example as been asked by a quick tour here. So there's a code, and I'll show some of the results. I'll prepared everything to save time because time is precious in this work, but you get a feeling by looking at the code. Can you see well? Is it in good resolution so everyone can see? Is it very visible? Do you want me to make bigger? It's important that you can read the screen.
I think it's okay, Gilberto. We can read it.
It's okay.
Okay, good. So basically, this is the R version. There is a Python version, but I'll concentrate on the R version. Essentially, you load, normally here you load the packages, and you create a temporary directory where you're going to store your data. Normally here, you start somewhere. And what normally you start is with a set of samples. A set of samples is what you obtain either by going in the field or by going, looking at the screen and identifying samples that you want. In this case, these are field samples collected by INPE in the place where I think IBGE people know well, Luiz Eduardo Magalhães. This is a very productive area in the state of Bahia. So we have a number of samples, and these samples here come with information, and Sophie has emphasized this. You must know what is the right latitude and longitude and to much more degrees. This is only showing 1 decimal point, but you need more decimal points here, which is hidden. A validity date and the label. The start date and the end date normally has the agricultural calendar, and the label corresponds to the land use or land cover in the agricultural calendar. So time, location matches label. So we have 2,300 samples divided in this case. This is a simple example, 4 classes. Cerrado, which is the natural savannas in Brazil. Cropland 1 cycle, which is temporary agriculture, mostly soybeans planted on a single cycle. Cropland 2 cycles here, and pasture. And here you say this was, you can see that was a field campaign because this Luiz Eduardo Magalhães in Bahia, and the people have gone to they basically went to one of the single producing areas and want to extrapolate to the others. This was like a windshield survey, which they come along, and here they sampled crop one cycle, and then there's more samples here along the road. You can clearly see that there was a road that the data collectors went, and they also collected some points. Basically, this was done by laboratory satellite on pasture. So I don't know if it's too big, put it this way. So here, once you have the samples, you can define, if you don't have a crop mask, in this case we didn't have a crop mask, but in this case a crop mask was not strictly needed. But you can say, for example, I want to find the bounding box of my data, which is, for example, I take the maximum latitude, the minimum latitude, the maximum longitude, and the max minimum longitude. So I have what we call a region of interest for this data set. And in this case, we define a data cube in the Brazil Data Cube repository based on this region of interest. So you say, okay, I want to be able, I selected one collection, could be this, in this case is CEBS, could be other collection, could be Landsat, Sentinel, whatever, in this region of interest. And the area in this case is smaller than the image. So in the Brazil Data Cube, unlike the other data cubes, there is no need to build regular data cubes. All the data cubes in the Brazil Data Cube are already regular. So this is already a filtered and cloud processed CEBS WFI. And for those of you who don't know WFI is a useful sensor that we use a lot for the deter program. It has 60-meter resolution with 800 kilometer swath. So this is a wide swath sensor designed to help us identify quick changes in the Amazon. So this has been extrapolated. Normally you have one of these every 3 days. So by combining them into 16-day interval, you get a nice cloud-free, mostly cloud-free images. So this is the next step here. So we copy this to a local interest and we show. So this is the area. This is the NDVI. So you have the NDVI. Here, basically, I'm saying, show me the area, in this case, for 30th of September of 2013, which happens to be the area of least cloud cover in the region. So you can see clearly a concentration of high NDVI or low NDVI, because this is just before the start of the sowing season. So the NDVI is low, and in the Cerrado, the NDVI is clearly high, because that's an area which is still not, it's still starting from the dry season, but it still contains a high NDVI. So here you have a description of your data cube, and in the end, these are images. So the data cube is a metadata that describes a set of images that are organized nicely by 16-day with a certain number of rows and columns and files. So you could actually stop here using SITs and go on, for example, your favorite program that processes TIFF files. You can, so the idea of being modular is that you can mix and match what you get from the SITs package with other packages that you want. So it's not like a single application, but rather as a very modular thing. And here you get the timeline. The timeline is exactly what you expect. Starts in 30th of September and goes every 16 days. Next 16 days, 16th of October, 1st of November, and so on. So there are 24 intervals with a temporal difference of 16 days. So these are regular intervals, and that's very important for the classifier. So, like I said, to obtain the time series, we need this information, okay? So we now have the data cube, which I showed you before. We have the set of samples. The next step is to get the time series from the samples. There is a function that says sits get data. So you get the data from the cube and obtain the time series. So the whole idea here is that you want to get this from each pixel that you have a label, you obtain a time series. So all of these, let's say, green pixels here, supposedly are pixels that you have a label. You know what the label is. The label may be pasture, the label may be cerrado, the label may be cropland. And in this way, you use these labels to train the classifier. So after you obtain the data, here again, this is, for example, so you get the data. That was, wait, this was me here. So this is the data set that you obtain. So this is the data set that you obtain by doing, let me see, I was here. So this is obtained when you get the SITS get data. And for what you get, it's for each point of the time, each location, a time series of EVI. In this case, EVI and DVI could be any other bands, Sentinel bands or CEBD bands, whatever data you have. And you can have the distribution of data, in this case, using a command known in R as summary. Summary tells you what you have. And it tells you that you have 136 labeled points for the class Cerrado. You have 1,250 labels for the class Cropland, one cycle. You have 790 for the class Cropland, 2 cycles. And you have 123 samples for the class Pasture. This is an undesirable situation because the data set is highly unbalanced. There are 50% of the points, 54% of the points belong to a single class. So this is not the best way to go. So SITS provides a function called SITS reduce imbalance. So SITS reduce imbalance, what it does, it increases the number of samples to a certain minimum and decreases the number of big classes with big samples to a certain maximum. Here we set up the minimum should be 150 samples, the maximum should be 300 samples. So when we reduce the imbalance of the data set, we get something like this. 150 samples for one and 320 for cropland, 324 for cropland 2 cycles. So this is a much more balanced data set and much more likely to produce good results. And here we can show the distribution of the samples for each class. In this case, I'm getting the class cropland 2 cycles, and I'm showing the NDVI band, and this is what you see. So clearly here, you see the red, so the dark brown curve is the median value of all pixels for each date. The yellow, dark yellow, are the first interquartile distance and the third interquartile distance. So this basically shows that this data has a certain coherence, and the blue ones are the full data. So you have here 324 blue lines, one dark brown line, and 2 light yellow lines. And you can see a peak. What is this peak? This peak is the data that is coming from highly cloud-covered data sets in December, no, mostly November, December. But the average is still, or the median is still clearly showing a 2 cycle. And again, like I stress, time series are by consensus now emerging as a way to use remote sensing for agricultural statistics. So the next step is to train the algorithm. And we offer a large number of algorithms and a simple way to train them. There is a function called sits train, where you say, oh, here are my samples. These are the balanced samples, which I referred before. And then this is my method. My method in this example is sits R4, which is sits rainforest, or random forest. And here you get, let me make it bigger. This is the distribution of the most important variables. And if you look, the numbers are small, so I'll spell it out. These are, in the top one is the most important value by its average position in the forests. So NDVI 18 means the NDVI band at the 18th instances. There are 24 instances, so you have to count, go back here to the timeline to find out what is the 18th instance. Where is the timeline? So, oops, sorry, too much. What's the time? So this is something 16, 17, 18. 25 of June of 2020. So 25 of June of 2020 is a very informative date. The NDVI of 25 of June of 2020 is a very informative date. And why is this an informative date? You can see that that's exactly the minimum point where separates the sowing of the first cycle of the cropland to the planting of the second cycle of the cropland. So some points are more informative than others. And this is the case of this point. And of course, points are the combination of dates and points is established by the random forest algorithm as a means of distinguishing the classes. So after you have now a model, you then just say, okay, let me classify the data. But the classification of the cube does not produce a map. Rather, it produces a probability. Why? Because the output of a machine learning classifier is not a map, it's a set of probabilities. And this set of probabilities is very useful, for example, to compute uncertainty, for example, to compute ensemble modeling. And in our case, one thing that's very useful is to remove outliers. There are many outliers, and these outliers are mostly places which are wrongly or pixels or pixel where the classifier or pixel where the data had an error located near pixels with high probability. So we do a Bayesian smoothing, a spatial Bayesian smoothing to clean. So it's maybe not obvious here in the screen for you to see that this data set, which is the output of the random forest, is much more noisy than the clean data set. But that's exactly the case. There's a recent paper we published on this. Okay, so after you have the smoothed, you have now included in the data the spatial information. Up to now, up to this point, we have been working only with the temporal information, so a time series. But the smoothing introduced the spatial domain. So the spatial domain now comes, and of course, the idea of that near things are similar, the Topler's first law of geography, comes in handy here, where this property of geographical data is used to smoothen the data. And after that, we can produce a map, in this case, a simple map of cropland 1 cycle, cropland 2 cycles, pasture and cerrado. And this is a step-by-step procedure. I won't go into much detail. I'm afraid of the time I have. I'm going to highlight 2 or 3 other points and sits, which are, important to highlight. One of them is the use of what we call self-organized maps, so it's too big, for control. Essentially here, going already to show, we have a very dense data set of 50,000 samples of the Brazilian Cerrado. And with the different classes, dense woodland is cerradão, dunes, fallow cotton, pousio, algodão, millet cotton, milheto, algodão, pasture, rocky savana, savana rochosa, ou savana estépica, savana propriamente, cerrado propriamente dito, savana parkland, savana parque, silvicultura, soja, milho, soy corn, soja, algodão, soy cotton, soy fallow, soja, pousio. And this is too big a data for us to understand well. So the SOM map provides a way to cluster these data and to identify samples which may be incorrectly labeled from one class to another. It's imagine that you have a big bag of apples you want, and it's so big you want really to find the bad apples and just keep the good apples. So this is really something that you should wonder when you work with lots of data sets. In the SOM map, and I don't have time to go into the details, but it's all documented in the paper and in the book, is an absolutely helpful way to deal with such big data that you can really use them from the point of view of selecting the data. You can measure confusion between labels, and this is, for example, the example here. This is a plot that was actually proposed by one of our colleague, Stefania Pizarro from Chile. And you can see here what we call the presage of confusion. So dunes are not confused with anything. Dunes are dunes. Rocky savanna is mostly rocky savanna. Fine. But soy fallow, for example, there's a confusion. 88% of the samples of soy fallow are okay, but 8% of them are confused with soy corn. And 3 of them are confused with 8% with soy cotton and 3% with soy corn, and so on. And we know what are the problematic ones. Some of the problematic ones, for example, savanna parkland is, as you would expect, a confused class. It's not easy to distinguish between savanna parkland from savanna. In the end, these two are very slow variations of the same, and therefore there is confusion here. And fallow cotton is a class which is really, really difficult, or at least it's difficult by itself, and the samples didn't help because there's a huge amount of confusion in the fallow cotton class. So this is the kind of thing that's a tool to rapidly analyze the quality of your data sets and the kind of confusion that you have. And then you can detect the noisy samples and improve substantially. Now, if you clean up, you get this. The good side of it is that you only have now clean samples, but of course, it may need, and this is a very thing that you learn in time, may need to retrain your data set. It may tell you, look, the samples we have for certain classes are not good enough. These are the classes that you can trust, but there are other classes which you need to go back and train. Now, this is one point. The other point, 2 points that I still want to make is, let me go slowly. There's a lot in SITS, a lot. Other points, for example, is the set of machine learning algorithms. So we have a number of machine learning algorithms. They include random forest, which is well known. They include the support vector machine. They include extreme gradient boosting. They include the traditional multi-layer perceptron. They include the temporal convolution neural network, which is it's a deep learning algorithm specifically for time series. And they also include some attention-based models, which attention-based models is what we call the most highly interested kind of data set, which is very much used as a backbone of ChatGPT. One other important use that we have is uncertainty. Uncertainty is not it's not quality control. And here, this is the uncertainty of your classification, which means that if you classify something, is there some areas, for example, here is an area near Samuel Reserve in Rondônia. And in this simple example, we had some samples of deforested areas and clean areas and had water, but we didn't have wetlands. And in this case, during the wet season, the Samuel Dam is full with wetlands, and in the dry season, it dries. And the classifier, not knowing this, classifies all of these areas as burned area. And this is strange. So when you ask the system, how certain are you of this classification? So this is what you get from the output of the classifier. The classifier tells you, this area in red, I'm very uncertain that I have classified it well. Oh, okay, so we need to put samples in this side. This is the area where we need to put samples to improve the classification. And yes, we put samples on this classification. We put more samples, for example, saying of the class wetlands, and then we classify it again. And then here we classify and we get wetlands, right? And then again, we ask the classifier, okay, how certain you are of this? Oh, there are areas which are very certain. I'm still uncertain in certain places here, but at least, so this is what we call active learning. You use the uncertainty of the classifier to improve the samples. Finally, one thing that we're taking care, but we need to do better, is to do the validation and accuracy. The validation accuracy is done currently using Cochrane's method for stratified random sampling. So essentially, we determine the number of samples to measure accuracy. So we have a map, and we want to find the accuracy of this map. And then we first determine, based on the standard error of the accuracy estimate, the standard deviation of the class obtained by the classifier. We then allocate the number of classes, and then we make what we call a sampling design. A sampling design is saying, okay, I have specified users' accuracy for each of the classes. I want to allocate a minimum of 100 samples for accuracy. I want a standard error of 0.98%. I want to take into account the rare class proportion. So here, I basically design. This is what comes out of this. It's a sampling design. It's the number of samples that I have to prepare for each class, based on the assumptions stated by Cochrane's formula. And this leads me, so I then use this to have a function called sit stratified sampling, which is put the samples in the place, and then you do the accuracy estimate by the traditional methods, which are stated in the literature, and the FAO literature, Wolofson et al. Okay, so this is like, stop sharing. So this is like a brief tour of SITS. The important thing here, this is an operational package. This is maintained by a group of programmers and researchers. And this is used in Brazil to do operational work in Terra Class, the the classification. This is going to be used now in PRODES, the classification of the Amazon. This is now being used also in Chile and Peru, in some countries. And we hope to, of course, make it, we are, as any open source developers, very much available to interact with anyone who proposes new functions. We have received many requests for new functions. We have even received contributions of code, which we welcome very much. So it's in a package which is open to contributions, and we hope that this provides a service for the community. Thank you very much.
Thank you very much, Gilberto. That was a very clear demonstration and a great example of how the SEEDS package can make the process of Earth observation data accessible and scalable. We included the link to access the book in the chart for those interested. And now let's take a short break. We will be back at 10:50. The next presentation will be with Professor Zigao from China, who will present use case and contributions to the UN handbook. So we come back in a few minutes. Professor Gao, are you with us?
Hello, can you hear me?
Oh, that's good.
So
I'm good. I'm pleased to introduce now Professor Zigao. He is a full professor and doctoral supervisor at the School of Remote Sensing and Information Engineering at Wuhan University. He has been recognized by prestigious talent programs in China and serves as a Chuchan Scholar, distinguished professor in Hubei province. Professor Gao research focus on remote sensing, Earth surface anomaly detection, multi-agent localization in complex environments, and visual data analysis under severe conditions. His work has been published in leading journals in computer vision, geoscience, and remote sensing. We are honored to have you here, Professor Gao, and the floor is yours.
Okay, thank you so much for the nice introduction. Actually, I will introduce my presentation. I will try to share my screen. Hold on.
Okay.
Oh my God. Can you guys see my screen?
Yes, perfect.
Okay. Dear, this is my great pleasure to be here to share some of my information with you guys. Actually, yesterday I already do a quick presentation about the research, mostly about myself, my team. Now today I should introduce some of our work contribution for the UN handbook on remote sensing for agricultural statistics. Actually, I do this quick introduction on behalf of our China team, including Beijing Normal University and Wuhan University. Okay, maybe just very quick introduce. Of course, in China now is already June 7 now, so the date is June 7. Of course, in Brazil, it's still June 6th. Okay, as in the first day, Gilberto already clarified several issues about the task, the work that the China team should plan to contribute, but not much information provided yet. After that, actually, I do a quick communication with China, our friends, our team in China, and to do some information collection and of course some progress update. I think Gilberto maybe be a little bit more confidence about the progress. Here I just list some chapters. For example, chapter two, our friends, Professor Pan Yao Zhong will contribute some content, including the optical and SAR data and processing related work in China into this chapter. In chapter 3, Professor Li Qiangzi and Huang Jianfeng will contribute to crop type classification in China and also crop yield estimation in China. Of course, for chapter 7, UAV applications, of course, our expert from also Beijing Normal University and another university, Professor Zhang Jingshui and Ma Xingming will contribute to the UAV-based applications. Of course, I and my team will contribute to the disaster response. Okay, in chapter 2, we already decided the focus. We introduce the China's GF series satellites. GF in Chinese, this is some short written in Chinese. The meaning is high resolution satellite. Then this work will be done by Professor Pan and his team member. And about chapter 3, crop type classification in China, and then this is more detailed section information. Firstly, 3.6.1, it is about winter wheat identification based on Sentinel-2 images and random forest algorithm. Then next subsection is about remote sensing identification of corn and rice in northern Jiangsu province based on univariate feature selection, and then vineyard identification by integrating continuous wavelet transform and a convolutional neural network. This is about chapter 2 and chapter 3, the contribution from China's side. Of course, chapter 4 is about crop yield estimation in China, and then mostly we first will contribute the remote sensing estimation of wheat yield based on photosynthesis models, and then remote sensing estimation of soybean yield based on multi-scenario simulation, and then remote sensing estimation of sugarcane yield based on the improved CEFI model. CEFI model, this is the name of the model called CEFI sugar. And then chapter 7, first, of course, is about UAV applications. First, the case is application of drones in farmland identification. And case 2 is about application of drone in crop identification. Case 3 is application of drones in greenhouse monitoring, and case 4, application of drone in crop disaster management. And case 5 is application of drone in crop yield estimation, and also some other cases can be chosen for the handbook. It depends on the editors and decision. Of course, for me, it's a layout, it's a main structure of the disaster response, introduction, key concepts and definition, and remote sensing for rapid disaster assessment, and then workflow for disaster response in agricultural areas. And section 5, practical methods and indicators, of course, and some data access and tools. 7 is cases, of course, for including some an automated flood detection algorithm for post-disaster assessment, and also an automated crop lodging detection algorithm for post-disaster assessment. This is the main content or main structure of the chapter 8. This is the main content of the chapters that our China team plan to contribute. Here, I still need a few minutes, then to take in chapter 7 as the example to show you some case applications we already prepared, but I think definitely based on previous days, Gilberto's requirements and introduction, and also the suggestion from the working team. Personally, I'm more clear about the requirements of the use case, what can be defined as use case, and what's the quality requirement that will be included in the handbook. It means our readers or users can reproduce the same results. We should achieve such kind of level, then can be defined as use case in our handbook. I will share another screen, okay?
Okay. Thank you,
Okay,
Professor.
I will share another file. Just quickly, maybe Gilberto or other friends can provide more comments and suggestions.
Okay, I think if I want to react, I would like to thank Professor Gao.
Excuse me, Gilberto and Marina, can you see my screen?
Okay, good, very good, thank you. Continue.
Okay, maybe I do not want to go to more details in our in this document for chapter 7. I think our colleagues or our friends, team member already prepare some sections. For example, case 1, UAV-based agriculture cultivation field particles, puzzles. For example, UAV-based CFPs identification, and also UAV-based crop type classification, and of course, UAV-based greenhouse monitoring, and UAV-based crop disaster assessment. And then, of course, this is the UAV-based crop yield estimation. Okay, more specifically, I take case 5, UAV-based crop yield estimation as a short example to show you what I have written in this sub section. For example, of course, for this case, we include introduction section and then also the methodology, the area, image data collection, and then the group ground truth data collection, and the index calculation and the data processing. I think all these must be shared with the original data, and some training code the code must be provided together with our book chapter. And for yes, estimation model construction, and then provide some results. This is and then conclusions. Okay, this is mostly about my presentation today. Firstly, I introduce the overall progress and overall requirement of the China's team's work or what China team plan to contribute. And then I take the UAV application as an example. Specifically, I take the UAV-based crop estimation as an example, as a specific example to show what the Chinese experts or the Chinese team have done. I know much work must be improved, not only the specific work, but and also the communication mechanism and the communication uh, skills also should be improved and updated to facilitate our handbook preparation. Okay, that's all. That's all my presentation. Thank you. Gilberto, your comments and suggestions are definitely welcomed. I will also record such suggestions and comments. Okay.
Yes, thank you very much. Just for the benefit of the audience who might not be fully aware of what we're talking about, the United Nations Big Data Hub and the United Nations Statistical Division, with the financial assistance and the guidance from the China Data Hub, have decided to, and the guidance of Ronald Jensen from UN and Lorenzo De Simone from FAO, have decided to produce a UN handbook on agricultural statistics. And we have invited many distinguished authors worldwide to act as authors on this book. And Professor Zigao just described. He's, of course, a very distinguished author, which we are delighted to have on his book, a very distinguished scholar. But he also described many of the contributions, very important contributions, that are going to be done by the China Hub team. I also might mention that we will provide via Maria Luisa a link to the handbook, as it's planned to be launched in November in Guangzhou in China. And so the handbook is not ready yet. It's an ongoing work, but I have to thank in advance some of the people who are here on this audience who are authors: Sophie Bontin, Lorenzo De Simone, Professor Gao, Stefania Pizarro, and Jonathan from INE Chile, and Claudio Stenner, who also will be an author, Ian Nunes from IBGE, who will also be an author. And I hate to forget people, but I hope that at least it's clear that we are taking a large chunk of contributions from people who are really involved in this effort for the UN Big Data Hub. And I have felt the not envious task of being the editor of the book, But given such high level of contributors from China and from other countries, this is not going to be backbreaking work. I think I'm trusting my authors very much, and I know that what's going to come out is going to be a very good quality. Thank you very much, Professor Gao, for this update.
Thank you so much.
Most welcome, and please thank your Chinese colleagues for helping so much. And of course, it's a pleasure always to work with China, as I have done so many years.
Okay, thank you. Got it.
Thank you, Professor Gal. Thank you, Gilberto, for the explanations on this collaborative work with the handbook. And as a regional hub, we are committed to share with the community the handbook as soon as it is ready. So now let's move on to our final panel with Lorenzo De Simone. Lorenzo, as I said, is as a technical advisor on geospatial issues at FAO, with deep involvement in the integration of AI and EO into agricultural statistics. Lorenzo, over to you.
Thank you very much, Maria, and thank you, esteemed colleagues. It's an honor, and I'm humbled to be here today with you. I'm just trying to open my presentation. I have to admit that after the excellent presentations today, it's more difficult for me to add value, okay? Because colleagues have gone into the details of the various aspects that collectively make the data production chain from Earth observation to statistics. So in any case, I will be happy to review together some of, let's say, my contribution, let's say, regarding the view on what's changing now, why statistics can benefit from modernization, how Earth observation and AI can be a game changer, some examples of applications. So we call that EO and NI in action, but then also, recalling principle of statistical soundness, and finally share with you some visions and takeaways. So we live in a changing world with new demands for data. In fact, we know there is an explosion in data demand. We want faster data, granular data, and real-time data. Policymakers need early warnings. They want seasonal outlooks. They look for subnational insights. And most importantly, we have drivers of this change, which is climate shocks, food price volatility, pandemics. They all put pressures on statistical systems. Of course, the statistical systems based on business as usual, they are affected by some limitations, such as slow cycles, high costs, and lack of spatial insights. So this is where Earth observation and artificial intelligence, they come in as a game changer, not just as a shortcut. First of all, let's first review what is Earth observation. So when we say Earth observations for statistics, of course, we're thinking of satellite data, Sentinel data, Landsat, MODIS. So we're not really thinking of just any remote sensing, which could be airborne orthophotos or handheld devices, but we really think of satellite images. So as we know, we have now wealth of satellites in orbit dedicated to Earth observation data. Nowadays, European Space Agency has more than 20 that are operational, and collectively we have almost 900 satellites in orbit, which are dedicated to Earth observation data. Another benefit and aspect of Earth observation is that it provides regular wall-to-wall coverage. So this is an example of the Sentinel-2 data, which is acquired at 219 kilometers worth. It has a 10 meters spatial resolutions. And the constellation is made by two twins, let's say, and it manages to cover the entire globe every 5 days. So you can assume that once you once you focus on your study area, you can have a revisit more or less every 5 days. Then there is a bit of variation depending on which latitude of the world you are, but more or less 5 is the average. Next, of course, what what does the satellite data do for us? What does Earth observation via satellite do for us? So again, this is an example from Sentinel-2. So the Sentinel-2 and the satellite image in general, they acquire the reflectance, so the energy of the sun reflected by the surface in the different bands. And based on the analysis of those bands, we can monitor vegetation, we can monitor and classify land cover, we can monitor drought, we can monitor flood. So this gives a lot of real-world application for statistics and also beyond. So I'm just giving you an example. We're all familiar with land cover classification. So this is a land cover map for Zimbabwe. So imagine we zoom in an area where we have prevalence of agriculture in this light brown. Now this is very generic and does not really allow to make statistics on crops. But if we use very high resolution satellite image and computer vision techniques, segmentation, we can already detect the field boundaries. And this is already important for many applications like area, for instance, farmer registries, and so on. Secondly, we can use then the time series analysis of the spectral information coming from the satellite image acquired every 5 days in the case of Sentinel to distinguish the behavior of the phenology and then to distinguish the different type of crops, integrating, of course, this information with field observations. Furthermore, so based on this, we can, of course, already start to extract area indicators. We're not there yet with the acreage, but at least we have a sense of where are the crops, which crops, and when they are actively being cropped in a country. Then we can integrate further this with physical-based crop yield model or data-driven crop yield model. There are different ways to do it, but to do this, what I'm trying to say is that we can further specialize and now have the crop yield estimation at the pixel level, at the plot level. And when we do this consistently in time within a standardized framework, then you can see how you can use Earth observation data to support the production of time series area, yield, and production. Furthermore, because we can detect also flood, we can detect drought. So in a geospatially explicit manner, this information can be overlaid with the crop type data, and then we can use this to assess the impact on the yield. So on the harvested area and finally on the yield, which is relevant for statistics. So let's talk now about artificial intelligence. What does it do for us? Well, fundamentally, as in general it does, it helps to automate processes. And in our case, it can help to automate and to speed up the analysis of the time series. It can help us to automatically clean in situ data, so the data coming from the field observations through either agricultural surveys, census, or ad hoc surveys. It helps in pattern recognition. It can help in segmentation. And overall, it can enable in scaling up the monitoring, basically, of the vegetation. Now, leveraging on Gilberto's slides, where he's simplifying the typical workflow used to go from satellite images to a classified map, so from which then we would extract statistics. So artificial intelligence is really helping us in each of those steps. In the creation of an Earth observation data cube, so going from scattered images to a regularized data cube. It can help us even to downscale the resolution of satellite images, so and even to intensify artificially the density of our time series. It can help us to infer on the quality of the samples we've collected in the field based on spectral characteristics. And then AI is used to train the model. So usually those classification models, they are AI algorithms like deep neural networks, convolutional neural networks, and so on. So this is a bit the landscape where AI is helping us in this domain. But of course, there are then further AI applications that benefit from geospatial data to inform farmers, for instance, on the optimal use of water, of fertilizers, and so on. Let's just focus for the time being for the statistics. However, there are some myths to bust because it seems that so nice Earth observation data AI will give us the statistics of the future. In reality, it's not so easy. It's quite difficult. But it is possible. The important thing is that we are aware of the limitations and we try to address them. So first of all, Earth observation data and AI, they are not like magic black boxes. There are limitations to AI and machine learning and Earth observation data, and it's always important to have human interpretability of models and of results. There is a risk in treating Earth observation models as ground truth, and we need instead to stress the need for uncertainty quantification. And of course, we need the ground truth data in the end. So we don't see the substitution of field observations, we see an integration. EO and NI, so don't replace the surveys. They can guide, optimize, and validate the data coming from the survey. And in this sense, it can be used to modernize the statistical design and quality control, and it's not going to substitute the official methodologies. It can be used to support and stratify the surveys, for instance. We can use a good crop type map to stratify our crop types in order to inform the area frame on where to sample in primary and secondary units, sampling units. And then it can accelerate the in situ data quality assurance and sampling frame optimization. Finally, the message is really blending new data sources, EO, with traditional methods. Then together that is going to lead to smarter statistics. So we can have this integration to increase statistical relevance, coverage, and timeliness. And it's about augmentation. And of course, the UN handbook is advocating really to combine EO with NSO's workflow through hybrid approaches. And finally, Earth observation boosts crop production data quality while it's combined with surveys and farmer records. This is a bit of references to support those statements. So in a nutshell, Earth observation plus AI plus official statistics are a winning recipe where EO is providing data coming in near real time. AI is facilitating the process of analyzing and extracting intelligence from the data, and statistics frameworks and protocols, they give relevance and rigor to those methods so that when we can assess the error, quantify the bias, and then make use of those maps or geospatial outputs for statistical systems. So altogether, they can enhance national survey systems, but in general, national statistical systems. Now I'd like to share just some examples of the applications from Earth observations for statistics. Many of these have also been covered by our colleague Sophie Bontam, so there's going to be some repetition of concepts, but I think, repetita juvent. So main cases for Earth observation data for agricultural statistics is economic efficiency. We can decrease the coefficient of variation, the error in area estimate by integrating field survey with crop type maps. We can increase the granularity of our statistics so we can disaggregate more below district level. We can have an estimate, an early estimate of the area of the crop acreage before the official statistical bulletins. It can inform the sampling design. So in theory, we should be able to sample less and sample better. And it should also be able to inform the response design. And after the data, the field survey campaign, it should help us to do the data quality control in automatic. So if we think about large surveys where we have thousands and thousands of data points, having EO and AI informing us on which are the samples which bring noise automatically and get rid of them, or at least raise flags, it's a huge help. Because in the end, the quality of the in situ data for the training and validation for the training, especially of the classification model, is the main responsible of the final quality of the crop type map. And of course, some SDG indicators can be measured totally or partially using geospatial data. And as we saw before, geospatial data also is useful for drought and flood mapping. So in general, disaster risk reduction. The examples I'm going to mention, they stem from the experience of FAO in countries in collaboration with many partners, among which University of Louvain, and of course, European Space Agency and GeoGLAM. And we start in 2019 with 2 countries, and now we work almost in 21 countries. We have also some new countries joining now in this year in 2025. The program is focused on capacity building, so it's really focused on co-designing solutions and then let the country run the solution on their own after the capacity building. Some examples. So the first example is sampling frame creation. This has been implemented in Zimbabwe, and essentially here we are merging a land cover map to create our area frame, to create strata based on agricultural intensity. And then we use the Cochrane's formula to assess the number of samples that we want to collect for each agricultural intensity stratification. And of course, we have the primary sampling unit, and then within each primary sampling unit, the secondary sampling unit. So this falls into the sampling design use case. This is a slide that Sophia has already very eloquently presented. Field boundary delineation. So this is the case of AMIS farmer registry in Rwanda. So Rwanda is really keen in establishing its own registry because they want to know who are the farmers and they want to know who is benefiting from the subsidies and to inform also the policy to target the right type of farmers. And of course, in this, they need to link the farmer to the actual plot that the farmer is managing. And in this context, we've been using very high resolution data from Planet, and we've been using a ResUnet algorithm to segment essentially the parcels. So we've been doing this for the entire Rwanda landscape together with the Digital Earth Africa, and we produced 1.3 million crop field boundaries in automatic. And now we are through a validation process, and gradually the plots are being georeferenced. Actually, they're being linked to the farmer ID. Okay, so we can say that we are georeferencing now the farmer to the plots. This is what the workflow looks like from a high level. So we have a high resolution RGB image. Then we predict the field boundary probability. Then we have the instant segmentation results. So we have the polygons. And then we compare these with the manually designed digitized polygons to assess basically the coherence, so intersection over union metrics. This is a very important application in many countries now because farmer registry are arising as the fundamental platform to regulate agriculture, to inform policy, and to provide services to farmers, but also to support field survey operations, to speed them up. So I'd like just to acknowledge the work that IBGE is carrying out. In particular, Jan Nunes is leading on the development of the field boundary across Brazil with the aim to support the implementation of the Census of Agriculture 2026. So this is really a draconian work. It's a huge size, but it's setting a very good example for many other countries. How we go about field boundaries in Zimbabwe. Then in Zimbabwe, we did not have so much support from AI and we did not have the infrastructure. So we took another road there. We joined the National University of Science and Technology, and where they cultivate a youth mapper club. So together with them, we organized a mapathon. We delivered training, and there was a manual digitizing context. Essentially, by the end of the 2 weeks' time, 320,000 crop fields were mapped, and now those crop fields, after validation, they've been already used by African Development Bank for the registration of farmers, but they now will be used to train a UNet model with the aim of mapping the rest of the boundaries inside the country. So this is a wall-to-wall map now of field boundaries across 6 districts that we have in Zimbabwe. Crop type mapping, no need to mention. Collaboration with University of Louvain, use of random forests, so machine learning classification system, and we developed the first national crop mask and crop type map for summer crops. We've learned a lot from the lessons about the quality, about the sampling design, and now we have collected the new data in 2025. So now we're able to improve the map and update the map. I would also like to acknowledge that the infrastructure that is hosting the solution is the National High Performance Computing Center. So as you can see, countries in the south of the world are starting to equip themselves with the right infrastructure so that they are independent from Amazon, they're independent from, let's say, external cloud providers. This is very important for the project sustainability. This is another collaboration with University of Louvain for the irrigated wheat in Ethiopia. Again, the work with the NSO and the Ministry of Agriculture is really to agree first on the data collection protocol, because it has to be probabilistic, it has to be, the response design must be well designed, and then finally we're able to produce irrigated wheat map. In this case, it's the white wheat, which you can see follows the morphology of the river, essentially. This is another example instead from a collaboration in Colombia. We've selected a specific area in Colombia where we have tried to improve the accuracy of the land use map. And this has been done through the application of time series data instead of a single image analysis. Professor Gilberto Camara has been really instrumental to introduce the time series through the seeds package, and this has shown how specific class could be immediately improved in their accuracy. Of course, there are classes where there is a need for further improvement, but this exercise was not supported by any additional data collection. So it was just about improving the algorithm, and already this showed improvements. Senegal 2019, this is the beginning of the EOSTAT project in collaboration with University of Louvain, and this was the first national crop type map, which was produced using a random forest within the Sen4Stat package. And it was used, basically, we used the available agricultural survey data from 2018, which of course was affected by many imperfections in terms of Earth observation requirements. So by the end of the day, this was the first national map, but of course it suffered from not very high overall accuracy for the crop type. I think it was around 70-75%, the overall accuracy of the map as it is. So we've been working with the country to improve the survey design, and we will see later in the presentation how this is now affecting the performance of the crop classification. Crop yield estimation, we've been using different type of models, in particular process-based models. It's a system of mathematical equations which simulate the soil, plant, and atmosphere systems, their interaction. And then it learns basically how the plant is responding to those conditions on a daily basis. So it simulates the crop growth. And of course, we need geospatial data to feed into the system climate, to feed into the system the crop type maps, where are the crops, information on soil, and then we need the information from the statistical office on the production or on the yield on a time series across years, so that we understand what has driven the yield up or down across the years, so that then we are able to predict in the future within different climatic scenarios, normal scenarios, drier scenarios, wetter scenarios, colder scenarios, hotter scenarios, and so on. This is how it works. So together with the Ministry of Agriculture in Ecuador, they've provided us with 15 years of crop yield data, with soil data, some climatic station data. And we've managed basically to train the model for 10 years, to calibrate it, and then to predict for the other 5 years, essentially, and to get very good results so that our crop yield model is able to get the same results, to match the results from the official statistics. This is now on Google Earth Engine, but of course, the power of this now is that the country, they can make an early forecast of the yield before the end of the season within different scenarios. And the former Minister of Agriculture, Bernardo Manzano, he attended the training himself, and he said that Ecuador is using this solution to inform early decisions on import and export quantity. So it's a very strategic application, but of course it has to be based on statistical robust foundation to be credible. Those are the simulations now done in Peru instead, with which we collaborate with the Midagri, with the Ministry of Agriculture. And you can see there is a good degree of agreement between predicted and observed. And of course, we have data which are not aligned along the diagonal. And what the work there is really with the crop modeler is to understand where are those areas where the model is not fitting well and why. So what is the data that is missing? Is there a problem in the model that does not really understand high-end yield or low-end yield? So this is a work of the calibration. So this to say that crop yield model in a geospatial explicit form and using a process-based approach, it requires a team engagement with the country, with the farmer extensions who know about the crops, with the institutions who study crops like CEMIT, for instance. I mean, you have many that do that, because you need basically to calibrate the model until it fits, and then you use it to predict. So this is the example of maize 2002, predicted in different conditions: cold conditions, dry conditions, hot conditions, normal weather, and wet. When we say normal weather, it means it's the average of the time series that we had to study basically the crop yield in time. This is again the predictions for rice, and this is the sugar cane. And now an example of how we use Earth observation data and AI for the policy feedback loop. And we refer actually to Peru, so to the last case for crop yield. Now, in Peru, we have the so-called Registry of Agricultural Producers, Farmers, the PPA, Padrón de Productores Agrarios. So more than 2 million farmers have already been registered. They wanted to create a producer database to distribute subsidies and to monitor who's using them. It's collecting 38 strategic georeference variables, and now the goal is to scale this up to 100% of the producers. And for these reasons, they have developed digital identity app. So the farmer wants to have subsidy, he wants to have access to credit, he needs to register, otherwise he cannot have those subsidies anymore. When he registers, in the app there is a geospatially enabled map where he can digitize his plot, or he can click on plots that are already pre-digitized, like the field boundary delineation. And once he does that, there is now a link between the individual, his person number, the services he's receiving, and the plots where there is activity ongoing. So this said, where does FAO basically come in here? So you can see those are the various applications that the farmer can benefit from if he registers. So the third one that I highlighted in red is reporting of damages for natural disasters. So the project with the Midagri there has been to the scope of the project with FAO has been to create a baseline information that is dynamic in time, that is quantitative on crop yield, so that when the farmer is asking for compensation and is declaring, I lost 2 tons of wheat, I lost 3 tons of wheat, because there are many farmers and you cannot control everyone, you cannot audit everyone, we want to have a system that is based on quantitative assessment of what is really feasible. So the crop yield model that is now geospatially explicit and it's at the national scale, it is used to establish where the farmer is living, so in that area, what is the specific farmer location productivity, but what also is the surrounding of the farmer, or what is the same profile of farmer, the production typical for the same profile. So he has, 3 plots, and the plots is this size. We look at similar situation in the geographical space, and we extract the crop yield from the underlying biophysical model. Okay. Similarly, African Development Bank in Zimbabwe is really now keen in knowing who are the farmers who received the subsidy and if their declaration are congruent. So we've put together now in Zimbabwe the crop type maps, the declaration from the farmers, the field boundaries, and we've developed the first prototype dashboard, which has been very much appreciated by the African Development Bank, and now they have intention to make this operational and scale it up to the entire country. So we are continuing in 2025. The project was also recognized by the GEO with the 2025 GEO SDG Awards ceremony that was celebrated in Rome. Now, finally, ensuring statistical soundness. So there is a need for rigorous and standardized validation of those outputs. Otherwise, a map is just, an artifact, and validation is not negotiable. So the Earth observation maps are models of reality, but it's not the ground truth. And so we need to validate to avoid misleading statistics. Probability-based sampling is very important. So the validation samples must not just be arbitrarily defined, but they have to follow probability logic, because this enables uncertainty estimation and avoids bias, as Sophie anticipated in her presentation and explained quite in detail. Accuracy metrics that matter, of course, we're not just happy with overall accuracy. We want to have class-based accuracy, area-adjusted metrics, confidence intervals, and integration of Earth observation data and field data to compute the statistics. So we really are no pixel counting movement. We really don't want that to happen. We want to stop that. We have some bias and black boxes. So deep models are powerful, but risk bias. Then we need more interpretable models and more transparent workflows. And in summary, you can't manage what you cannot validate, essentially. We recently co-authored a paper where we tried to define a framework to assess, for instance, the suitability of field survey data from agricultural survey, their fitness for Earth observation purposes, from both the probabilistic point of view, so the statistical point of view, but also from the Earth observation point of view, hence the spectral coherence of the data. This is the neurons which compete for pixels. This is an exemplification of the self-organizing map, which is one way to carry out the validation, the quality control of field survey observation from the spectral point of view. So what the system does, it uses Earth observation data coming in, machine learning to analyze the similarity of the spectral signatures of the various field observations, the labels, and it makes sure that data that are labeled with the same name are similar in the spectral space. So we expect all the wheat neurons to be close to each other, the barley to be close to each other, and we don't want instead to see those outliers. And what the system does very automatically, this is extracted from the work in Chile, from Estefania Pizarro et al. Essentially, it allows us this solution to immediately identify over thousands of data points, the points which are reliable, the one in blue, the points which require some attention, the one in yellow, and the ones that should be dropped, the one in red. So you can see how EO and NI is accelerating this process and is working towards statistical rigorous. This is simplification of the validation process. So we have the classified map. We use our validation data points. We build our confusion matrix. We measure commission and omission error. And then from there, basically, we extract the statistics, overall statistics, producer accuracy, consumer or user accuracy, kappa statistics, and F1. This slide, coming from the collaboration with the University of Louvain in Senegal, is now linked to the discussion we had before on the national Senegal map, which was affected by low accuracy due to the quality of the training data. So together with the Ministry of Agriculture, DAPSA, we've managed to implement an experimental adjusted survey design, meaning that now the parcels are being georeferenced, the boundaries, and the centroid. And this has been applied to Nioro district as a first prototype. And now the accuracy was above 90, let's say 90.2%, the overall accuracy. And the success of this exercise has been such that now the Ministry of Agriculture has decided to adopt this approach, so the adjusted protocol from the EOSTAT project, to other 6 districts. So now we have 6 districts that have conducted this type of survey. So we can see how, working together with the country, we can establish a robust field data collection system that is fit for both the statistical purpose, but also for Earth observation. And this is essential for the sustainability of crop type mapping, because now the country has a mechanism to collect the data and then produce the maps anytime they want. So that's the added value. We have to correct for the bias in area estimations. There are several methods to do it. There is a nice practical guide developed by FAO, by Ilenia Fingold some years ago, and it clearly explains how map accuracy assessment is to quantify the accuracy of the map and then to generate new area estimates to correct for bias in the map. But then methods have evolved. So we have also, okay, don't count pixel, that's take-home message, but I want to say that what Sophie Bontemps presented earlier on is really, a next step to the previous manual published some years ago. So the geospatial community and the statistical community have now stronger grounds to work together, because there has been quite good advances on how to transform the crop type map into statistics, working together with the field observations. This is the similar slide that Sophia has presented for Spain. Basically, we show that when we combine the crop type map with the field observation, and we recompute the proportion between the primary sampling unit, the proportion of the individual crops, basically we reduce the overall coefficient of variation, so the error, the uncertainty, without intensifying the sampling. So this is a cost efficiency gain. So what I want to say is that the good news is that all of this wealth of methods, not just to produce the map, but to collect data in the field, to verify the quality, to validate the map, to produce the map with the best pre-processing methods, or how to choose the algorithm, they're all condensed now together in the new handbook for remote sensing for agricultural statistics, which is under work in progress, with the collective contribution of international experts who decided to volunteer to this task. And the good news is that you will be able not just to reflect on the theories here, but actually to run the scripts for the specific use cases and eventually identify things that work better for your business. And then, of course, you can always reach out to the authors to support customization and further discussion. Finally, vision and takeaways from these 2 days of intensive exchanges. So my impression is that the future for statistics is going to be geospatial and intelligent, and therefore we will need to build systems that are dynamic, inclusive, and adaptive. Dynamic because we have new solutions coming, new sensors, new technologies. Inclusive because we need really to work together with different institutions. We cannot think that institutions alone can carry out all of the burden. If you think of farmer extension, field survey, high performance computing center, machine learning, you really realize Earth observation sector, the data providers. So we really look at an inclusive system, and of course adaptive, because no one single solution can fit every situation in the country. So the concept of agroecological zoning, to mention one of the conditions, but also the workflow of specific NSO. EO and AI are really the infrastructure now. So it's not anymore a nice to have thing, but it's really a must have for modern statistics. And of course, they need to be mainstreamed into NSO's workflows. So in order to be efficient. Somebody's knocking on my door. Sorry. There is a need to invest in capacity and not in dependency. So building skills, partnerships, and ownership, which is a bit, the spirit of the capacity building, especially in FAO, is that of co-designing solution, delivering technical capacity, and then taking steps back as the country is going to lead the solution. I'm almost finished. So the future of agricultural statistics is finally data-driven, geospatially enabled, intelligence-powered, quality-assured, and inclusive. So, obrigado. Vamos continuar juntos neste caminho de inovação e impacto. Obrigado.
Muito obrigado. Muito obrigada, Lorenzo. Thanks you very much. We have a question about from Mr. Roberto Azofeifa from Costa Rica. He's from the Agrometrics unit from the National Extension Program. He's asking how can we have more information about the Farmer Digital app?
Thank you very much. So, first of all, we will follow up via email. The Farmer Digital app is publicly available, is very much advertised in Peru. Plus, we collaborate directly with the director, Cesar Esteban, the director of one of the department in the Ministry of Agriculture, Midagri, who is leading on that. So we are very happy to make the connection, but we need to keep track of your email so that we can write to you. So I hope, Maria, you can help us to stay in touch with our colleagues. Okay.
Yes, of course. And thank you. So we still have some minutes for more questions. So please include the questions and your comments in the chat. Or if anyone wants to raise the hand, you'll be welcome. And can you use this moment to take a photo? So I'd like to invite all the specialists which were involved in the workshop who are available to turn on their cameras so we can capture a quick group photo. Lorenzo, can you please stop sharing so we can see everyone's cameras? Great. I have Eduardo, Stefania, Gilberto, Paulo, Cláudio, Sophie.
It's a group photo.
It's a group photo.
So we have to look good, right?
Yes. Smile. Okay. I'll make two because people are in different windows. So the first one, let's go. Okay. Wait a minute, I'm saving and let's take one more. Another one. Okay, guys, thank you very much.
Maria Luisa.
Sim.
When are you going to share the presentations, the video? You're going to announce this on the web or how's it going to be done?
We share the presentation. We share the recording of the webinar in our website.
Okay. So please remember to send us a line to that. Thank you very much.
Yes, of course.
And thank you for organizing everything. It was a pleasure to work with you and IBGE, and very much thanks from my side.
Thank you. Thank you very much, Gilberto. And I'd like to thank everyone. Let me see if there is... yes, people are sending saludos cordiales, the INEI from Peru, the Lima. They are saying hi. And so that's it. I'd like to make a wrap-up of this two-day webinar. I'd like to sincerely thank all of you who joined us, whether from Latin America and the Caribbean or from other parts of the world. We are very happy with the engagement of the public because it's truly remarkable that we had so many people connected both yesterday and today. Unfortunately, we did not have the possibility of offering simultaneous translation into Spanish, but your continued participation shows the strong interest from institutions across Latin America and the Caribbean in this methodology, and it also reflects the high quality of the presentations we have had. Thank you all so much. And also thank you to our incredible speakers and panelists. Your presentations and reflections have greatly enriched our understanding of how our observation and artificial intelligence can contribute to agricultural statistics, to the sustainability, to the food security, and all of the points that it's related to. And as Lorenzo, Gilberto, and Professor Gal mentioned, these discussions are part of an ongoing international effort to strengthen the UN Handbook on Remote Sensing for Agricultural Statistics, and also to foster collaboration across institutions and regions. And for us at IBGE and at the Regional Hub, it was a pleasure to receive this so special group of specialists this week here in Rio de Janeiro to discuss the handbook. And we are very grateful that they made time in the agenda to drop this webinar for our community. Thanks a lot. And we also thank our partners at UNSD and all my colleagues from the Regional Hub who are behind the scenes, who helped make this event possible. So thank you, Paulo Toches, Luiz Felipe Lousada, Bruno Herbich, and Yasmin, and also our colleague and student, Roberto Jacinto, that were with us this week. Thank you for all the support. And we hope to see you again the next session of our webinars on climate change indicators. On July next month, we are going to have another webinar. Until then, thank you once again, and goodbye, everyone. Bye-bye.
Bye.
Thank you, Maria. Thank you all.
Bye-bye.
See you.
Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.